Hello friends, welcome to the sixth session of this tutorial series, that is a complete design of a three-storied building using ETABS. If you have not watched my previous sessions, please do go ahead and watch them. So in today's session, we are going to design the footing of our building. To go ahead with the design of the footing, first we have to determine the reactions coming on the footing, and to obtain that there are two ways. The first one is by clicking on the 3D view screen and then select the display support and spring reaction. Then you can just select the load combination corresponding to which you need the reaction at the support. So let us assume we select dead load plus live load, and then we know that Fy and Fx, then Mx, My, Mz, these forces will not be there because it's an isolated footing. Fx and Fy will be there, but those will be in a minor amount, so we can neglect them. So just select this Fz and click apply. So we can see the reactions on all the footings. And to design the footing, we need to get the reaction corresponding to the most critical load combination. One way to do that is by selecting each load combination and clicking apply, and then noting the value of the reaction, and to select the value of the reaction which is having the maximum value. For example, for dead load, the value of reaction at this footing is 241 kilonewton. For dead load plus live load, it is 269, still higher. For, let us take 1.2 dead load, it is 289.95, still higher. And for, let us take 1.5 dead load plus 1.5 live load, it is coming around 403.89 kilonewton. And we can see that this is the most critical load combination, that is 1.5 dead load plus 1.5 live load, and we have to take the reaction corresponding to this load combination. But let us assume our building is 3-4 storied and we are giving earthquake load also, then the number of load combinations coming will be much higher than this. So it will be a time consuming to click on each load combination and then seeing which is having the higher value. So we'll go to the second way of getting the reactions more easily. For that, just click close and go to display, then show tables, then expand this analysis box, then the results box, and then click on this reactions. Then we'll click OK. Then a tabular column opens up. We can just expand it. Now here select design reactions. So this tabular column shows the entire reactions of all the load combinations and all the supports. Now we have to sort this out so that we can get the reaction at each of our footing more easily. For that, we'll go and select this join label and then right click here. Then we will select the first one, that is join label number 10. So it will show only the reactions corresponding to join label number 10. Then we will go to Fz, that is the vertical reaction that we require, and then click on it, and then right click on it, and we'll select sort descending. So it will show the forces in the descending order, and thus we can get the maximum reaction quite easily. Now to find the reaction at the next footing, just go and select this join label, then right click on it, then click on this join label number 11, and then again go to Fz and then right click it, then sort descending. Then we can get the maximum reaction from here, that is 374.93, and similarly we can get the reactions at all other supports. Now the next thing we need to note is that the joint label corresponding to ETABS and what it corresponds to us in our actual plan. So this is our actual plan, and in this we have marked this as C1, C2, C3, C4, C5, C6, C7 like that up till C14. For us this footing number is 1 and this is 2 and this is 3, this is 4 and likewise. But now we'll just close this as we now have learned how to get the maximum reaction at any support. So we'll just close it. On this 3D view, just put your cursor on this joint, that is this support, and then right click on it. It will show you label number 19. So for us in the actual drawing, this footing should come as number 1, but for ETABS it has named it as 19. And to see the second one, this is our footing number 2. Right click on it and it shows label number 20. Similarly, we know that this extreme footing is number 14 for us, and by just right clicking on it, you can know that for ETABS it is label number 10. So like that, we need to note down all the labels in the ETABS and corresponding column number which we have assigned in our actual plan. Now after we have noted down the maximum reaction at the support which we will be using in the design corresponding to our footing number, we can just tabulate it in an Excel sheet and it will look something like this. That is footing number 1 having a maximum factored reaction of 404 kilonewton, and then footing number 2 having a maximum reaction of 669 kilonewton, and so on. This is the Excel sheet which I have prepared, which will help us to design the isolated footing much faster, which we will come back to it after we have studied the concept behind the design of isolated footing. And if you want this Excel sheet of mine to design your isolated footing quite faster, you can just put your email in the comment section below and I will just mail it to you. So now let's go ahead and see how the design works. Let us take the footing number 1 having a factored load of 404 kilonewton, that is P factored is equal to 404 kilonewton, and the P value, that is the unfactored force, is given by 404 kilonewton by 1.5, that is the factor safety. So we get 269.3 kilonewton, and we have chosen the grade of concrete as M25, that is 25 Newton per mm square, and the grade of steel as Fe 500D, so Fy comes to 500 Newton per mm square. Let us assume the diameter of bar as 12 mm and the width of column as 200 mm. The width of the column in the other direction will also be 200 mm because we are taking a square column. And as per the site condition, I have QC, that is safe bearing capacity, as 400 kilonewton per meter square. And the depth of the footing from the ground surface is 1 meter. So first we have to calculate the area of the footing required. For calculating that, we will be using the formula 10% of P plus P divided by QC. This 10% of P we are taking to incorporate the dead load of the soil and that of the footing. So the value comes around 0.75 meter square, that is the area of the footing required. So we are taking it as a square footing. So the dimension of the footing is given by square root of 0.75, that is equal to 0.86 meter. So let us take the size of the footing as 0.9 meter by 0.9 meter. Next, to calculate the depth of the footing, that is the thickness of the footing required, we will be calculating it based upon one-way shear. The one-way shear we are calculating at a section which is at a distance of D from the face of the column. So we have this remaining length given as L minus A by 2 minus D, and Q is the uniform soil reaction. So the uniform soil reaction Q, that is the factored soil pressure, is given by the factored load coming on the column divided by the area of the footing actually provided. That is 404 kilonewton by 0.9 into 0.9 meter. It will come to 0.498 Newton per mm square. Next, the value of tau c, that is the shear strength of the concrete, we are taking it as 0.36 Newton per mm square. This we can obtain from IS 456 table number 19, that is you can find it on IS 456 page number 73, corresponding to the grade of the concrete, that is M25, and assuming the percentage of steel as less than 0.25, we will be getting a value of 0.36. Now, the shear force at this section XX is given by Q multiplied by L, that is the uniform soil reaction Q multiplied by this length, that is Q multiplied by L multiplied by this remaining length, that is given by L minus A by 2 minus D. And next, the shear force, that is the shear resistance of this footing, will be given by tau c, that is shear strength of the concrete, multiplied by this effective depth of the footing, that is D, multiplied by this length L. Now equating this equation number 1 and equation number 2, we will be getting the value of D, that is effective depth of the footing. So the effective depth of the footing, D, we will get it as 203.2 mm. Now next we have to check for two-way shear. Two-way shear we will be taking at a distance of D by 2 from the face of the column. So the factored shear force, we will get it as Q, that is the uniform soil reaction, which we calculated here, multiplied by L square minus A square plus D square, that is this area of the footing L square minus this area, that is A plus D the whole square. So the value will come to 322.8 kilonewton. Next, the shear strength of the concrete, from IS code we have a formula 0.25 root FCK. So we will get the value as 1.25 Newton per mm square, as FCK is 25. So the shear resistance of the concrete we can obtain by multiplying the strength of the concrete by depth of the footing D and the total length where the resistance is coming, that is the perimeter of this dotted line, that is 4 times A plus D. So we will get the value as 409.8 kilonewton. And comparing this value with the shear force actually coming, we can note that the shear force actually coming is 322, is less than the value of the shear resistance of the concrete. So our design is safe. Next, we will come to check for gross bearing capacity. The unit weight of concrete, we will take it as 24 kilonewton per meter square, and that of soil as 20 kilonewton per meter square. The gross bearing force is given by the density of the concrete multiplied by the volume of the concrete, that is 0.9 into 0.9, that is the area of the footing, multiplied by the depth of the footing, plus the density of the soil multiplied by the volume of the soil, that is area of the footing, the depth of the footing, that is 1 minus D, that is 1 meter is the footing depth at the base minus the thickness of the footing, that is D, plus the value of the force coming on the footing, that is 269.3. So we will get this value as 286.19, which is less than 400 kilonewton. That is our safe bearing capacity of our soil. So our design is safe. Next, the total thickness of the footing we have to provide is given by the effective thickness of the footing 203.2 mm plus the clear cover which is required, that is 50 mm. This is as per IS code for footing, plus the diameter of the bar and plus the diameter of the bar by 2. How this comes, I will show you in the below figure so that you can understand more clearly. So the value will come around 271.3 mm. So rounding it off, we will get it as 300 mm. That is the total thickness of the footing we have to provide. So now we have found out the dimensions of the footing required. Now next step is to find the area of the steel required for the footing. For that, we will be finding out the bending moment at this section XX, that is at the face of the column. It is because the bending moment will be maximum at this section. So at this section, the bending moment mu at section XX is given by total force, that is Q into L minus A by 2 multiplied by the lever arm, that is L minus A by 2 divided by 2. So calculating, we will get value of mu as 27.49 kilonewton meter. Now from IS 456 for under reinforced concrete, we have formula mu is equal to 0.87 Fi ASTD multiplied by 1 minus AST Fi by BDFCK. This formula you can find in page number 96 of IS 456 2000. Here it is. So now substituting the values in this formula, we can find out AST. The only unknown in this formula is AST. This will come to a quadratic equation and there will be two values for AST, that is area of steel. We will take the lesser value. So it will be 322.45 mm square. And from IS 456 we have a clause that minimum area of steel required should be 0.12% of the cross-sectional area, that is 0.12 by 100 into 900 into 300. This 900 is the dimension of the footing and 300 the total thickness of the footing, and the value is 324 mm square. So we have to provide a area of steel as 324 mm square because this is higher than this area of steel we have obtained from our calculations. This clause you can find from IS 456 page number 48, which is given here, the minimum reinforcement. Now to calculate the spacing of the bars, we have to provide spacing is given by L, that is the dimension of the footing, minus the clear cover on both sides, that is 50 and 50, minus diameter of the bar divided by the total number of bars minus 1. So we have spacing as 422.53 mm. But as per IS code, the maximum spacing cannot exceed 300 mm. This you can find from IS 456 page number 46. Here it is given the maximum distance between bars in tension. For slabs, as we are considering footing as slab only, it is given by not more than 3 times the effective depth of the slab, and in this case 3 times effective depth of the slab will come to 609 mm or 300 mm, whichever is smaller. So we will be taking as 300 mm because this is the smaller value. So we have to provide reinforcement as 12 mm dia bar at a distance of 300 mm center to center. And this is the drawing we'll be providing for understanding our design. So this bar is the bottom reinforcement bar, and this circles I have represented as the reinforcement bar in the opposite direction. The effective depth calculation which I have been talking to you earlier, we are finding as distance from the top surface of the concrete to the center of this top reinforcement bar. So the total depth is 300. So we got effective depth as 203.3. To obtain the total thickness, we have to add the half diameter of this bar plus the diameter of this bottom bar plus the clear cover. And next, to have a bonding of a column with this footing, we will be providing extra bars from the footing to the column, which should have at least a development length to have a proper bonding with our footing. So the formula of this we can obtain from IS 456 clause 26.2.1, and we will be providing a minimum of 3 stirrups in this area which is having a diameter of 8 mm and a spacing of 300 mm center to center. So this completes our design. So as you can see, this design is a lengthy procedure. So to shorten that time and to get the design in a faster way, we are using the aid of design Excel sheets, which you can create by yourself itself. So let me explain the Excel sheet which I have prepared. These are the forces we obtained from our ETABS, and these are the footing numbers. And this column is the design result, that is the size of the footing, the thickness of the footing, the total thickness of the footing it is, and the reinforcement required.
So, in design of an isolated column footing, what we are actually doing is finding out just the three parameters, that is the size of the footing, that is the dimension of the footing, that is the area of cross section of the footing, and the thickness of the footing required, and the reinforcement details. So, to find the size of the footing, what we are doing is just dividing the total load coming on the footing by the bearing capacity of the soil. So by just putting these values in here, that is the factored load, the grade of concrete, the grade of steel, the size of reinforcement bar, the column dimension, the safe bearing capacity of the soil, and the depth of the footing from the soil surface. And the size of the footing is calculated and is given here. Now, rounding off, we can enter a value slightly higher than the value we have obtained. Now next, what we have to find is the thickness of the footing. And the thickness of the footing we are finding out using one-way shear. So, by just putting the value of tau c, that is I have written as TC here, from IS code, we will get a value, the effective depth of the footing. Now there are two checks to verify the thickness of the footing that we have found out using one-way shear. That is check in two-way shear and gross bearing capacity check. If it is found safe, then you can go ahead with this depth of footing. Otherwise, you need to just increase the effective depth of the footing. So we have now found out size of the footing and thickness of the footing. Now the last parameter we need to find out is the reinforcement required. The reinforcement we are giving the footing because the concrete is not having the capacity to take the bending effect which is coming on the footing. So to take that bending effect only, we are providing the reinforcement. So we can calculate the reinforcement required by the bending moment coming on the footing. So with this help, we will get a value of steel required, and you can just cross check it with minimum area of steel required, and in this column we can input the higher value among these two, and with the help of Excel sheet you will get the spacing, and make sure that spacing is not greater than 300 mm, and the thickness, that is the total thickness of the footing, we will be getting here, and you can just round it off to a next higher value. Thus we have found out the reinforcement required also. So our design is complete in just 3 simple steps. Now in a similar way we can do the design of all our remaining footings, and we can tabulate the result here and just copy this result to another page, and we can give a note down below here that is giving the grade of the concrete, the grade of the steel, and the size of the diameter of bar, the depth of the footing, and also we can give a note that this reinforcement should be in both directions and the clear cover given should be of 50 mm. Now you can just take the printout of this design and give it for the site execution purpose along with the fair copy of the drawing. And how to prepare the fair copy of drawing to be given for site execution, we will be discussing at the end of our tutorial series.
And in our next tutorial, we will be seeing how we can design the column of our 3-storied building. And we are going to start an online ETABS workshop certification course very soon. So please do check it out. The link for which I have given in the description section below. And if you like this video, please don't forget to like, share and subscribe. And do leave your valuable comments in the comment section below. Thank you.